So the Board of Studies expect the hypotenuse, adjacent and opposite sides with respect to a given angle in a right angled triangle of any orientation be shown to the students, and that's what we'll go and do. So lesson 1 does that. It identifies the hypotenuse, adjacent and opposite sides with respect to theta. The board then requires that the labelling of the side lengths of a right angled triangle in relation to the given angle, e.g. side C opposite angle large C, and recognise that the ratio of matching sides in similar right angled triangles is constant for equal angles. And here is the second lesson addressing those points. The board requires that sine, cosine and tangent ratios for angles in right angled triangles are defined. The students know about that, and using the trigonometric notation such as sine A. And this is lesson 3, defining sine theta as opposite over hypotenuse, etc. for cos A and tan A. The students are then required to use calculators to find trig ratios for a given angle in degrees. Use the calculator to find the angles in the nearest degree, given one trigonometry ratio of the angle. And they're also required to select and use appropriate trig ratios in right angled triangles to find unknown sides, including the hypotenuse. Selecting and using appropriate trig ratios in right angled triangles to find unknown angles correct to the nearest degree. So basically the students have to learn how to use a calculator to calculate those degrees in minutes given the ratio of the sides. They have to be able to find an unknown side of a right angled triangle. Given that the angle is measured in degrees in minutes, they have to go back from there using the calculator or any other method. And they need to use the trig ratios to find unknown angles in degrees and minutes in right angled triangles. So basically my lesson 4 takes care of all of that. It's quite a bit of work here, so we'll just go through it. Most of the students will be using a Casio calculator such as this. There's an emulator available, so you can put it up on the screen, the big screen, and push the buttons with a mouse. And that's quite good for them to understand how to use their own calculator. So lesson 4 basically is a double period at least to cover these calculator problems. Here we have a part of an angle that has to be turned into minutes, degrees. So you can see here that the students are introduced to some of the nomenclature of trig, such as angle B, triangle ABC. Those symbols are important to know, and the perpendicular, they need to know that as well. Well, lesson 4 gets complicated a little bit because it introduces the inverse trig functions to the students, probably for the first time. They'll have to get their head around the use of the function, and I will be going through the use of the function and not the definition, because I think the definition, elaborating on it, will just confuse the students more. The cos and sine of right angled trig functions are complementary. The students need to know that. That's what the board requires. So the lesson 5 covers that material, plus it's a natural extension into the reflex angles 180 minus theta. So I introduced the students to a little bit of extended work in this lesson, in case they choose, some of them choose to go down the extended path from Year 9. So lesson 5 then goes through all stations to Central, and that'll give the kids a chance to remember which trig functions are positive in which quadrants. And just a couple of examples there of those complementary functions. So my lesson 6 is concerned with bearings and angles of elevation and depression. The board for some reason is insisting that that goes above, that they list it above some other parts of the trig, but I've always been taught that that's the way to do it, put it at the end. It makes sense to go at the end, so I've changed the order. And this is the end of lesson 6 and the end of the unit of work, where they're working on problems of real life bearings and angles of elevation. The later worksheet that I produce for the unit of work goes through a heap of exercises and examples, word problems, etc. on all of that unit of work. And that's it. Coherent lessons that are sequenced the right way and engaging. So I'm just picking out the engaging parts of the lesson plan for the unit of work that I completed. So the first part is I suppose the emulation of the Casio calculator on the interactive whiteboard would be the engaging source in this topic. In the same lesson, lesson 4, we talk about 360 degrees in a circle and how that was and how that came about, which is pretty interesting. And it looks like a kludge, doesn't it? Introducing real problems in the physical world, in the applied mathematics stream into the trigonometry. You can see here a skier going down the slope, and this forces act upon him, and to work out using trigonometry things about his motion. At the end of the unit of work, there's a little excursion arranged, and it's visiting Sydney Uni physics building in Science Road, I believe, or Physics Road, is it? Sydney University's physics building has 2 telescopes, radio telescopes on top of the building. One is a transmitter and one's a receiver, and you can actually line up these telescopes at the edge of the moon, so as the moon passes through the telescope while it's bouncing its radio beams, you can pick up a signal on the receiver and work out how wide the moon is, which is pretty good, and you can work out how far the moon is away from the Earth as well, very accurately, just using those 2 telescopes. And I thought that would be a good trigonometry excursion for the children. And just to the worksheet here, there's one problem here. You can see there's a graph of slow moving creatures, and which one is the slowest, which is the fastest. And this is where the syllabus is trying to get the Year 9 kids to understand trigonometry and scaffold them to the y equals mx plus b, which is a gradient form of the line. So that's why I introduced that problem. There's no numbers there, they just need to understand the rise over the run concept. And just finish off with an elevation problem there with a kangaroo standing a distance away from Uluru in Alice Springs. And just some interesting facts about Uluru. I didn't know it was that deep into the ground. I didn't know it goes that many kilometres into the ground, but they've got a bit of an estimate there, so that's quite interesting as well.